Welcome to today's session. We'll be diving into problem number 2165, titled Smallest Value of the Rearranged Number. In this problem, we'll explore an intriguing challenge that involves rearranging digits to achieve the smallest value. Get ready to learn and sharpen your problem-solving skills. In this problem, we are tasked with rearranging the digits of a given integer, number, to form the smallest possible integer. If the rearranged number has leading zeros, they must be removed, unless the number itself is zero. Additionally, if the input number is negative, the result must also be negative, and the digits should be arranged in descending order to achieve the smallest, or most negative, value. The input number can be any integer within the range of -10 to the power of 15 to 10 to the power of 15, and the output will be the smallest integer that can be formed by rearranging its digits. To clarify further, let's look at a few examples to understand how this works. For the first example, the input number is number equals 310. To find the smallest possible value, we rearrange the digits in ascending order, which gives us 013. However, leading zeros are not allowed, so we remove the 0 to obtain the output 103. This is the smallest integer that can be formed using the digits of 310. Now, in the second example, the input is number equals -7605. Since the number is negative, we need to arrange the digits in descending order to find the smallest, or most negative, value. Rearranging gives us -7650. This is the smallest possible value for the given input. To elaborate on the second example, the digits of -7605 are rearranged in descending order, resulting in 7650. After reapplying the negative sign, the output is -7650, which satisfies the requirement for the smallest value. In the third example, the input is number equals 0. Since the number is already 0, no rearrangement is needed, and the output remains 0. These examples help demonstrate how the problem handles both positive and negative numbers, as well as 0. Now let's take a look at the constraints and some important edge cases to keep in mind when solving this problem. There are a few key edge cases to consider. First, if the input number is 0, the output must also be 0, as no rearrangement is needed. Second, when rearranging positive numbers, any leading zeros resulting from sorting must be removed. For example, if number equals 1000, sorting the digits gives 0001, but the leading zeros are removed, resulting in 1. Third, for negative numbers, we need to handle them carefully by first removing the negative sign, sorting the digits in descending order, and then reapplying the negative sign to get the smallest value. Additionally, the solution must handle very large inputs efficiently, as the range extends from -10^15 to 10^15. Lastly, for single-digit inputs like 8 or -3, there are no digits to rearrange, so the input itself is the output. Keeping these cases in mind will help ensure the solution is robust and handles all possible scenarios. To solve the problem of finding the smallest value of a rearranged number, one approach we can consider is the brute force method. The idea here is to generate all possible permutations of the digits of the given number and then select the smallest valid number from them. To do this, we first convert the number to a string so that we can extract its digits. Then, we generate every possible arrangement of these digits. After that, we convert each permutation back into a number, making sure to ignore any leading zeros. Finally, we return the smallest number from the valid results. However, this approach comes with significant trade-offs. The time complexity is O(n), because the number of permutations grows factorially with the number of digits. Similarly, the space complexity is also O(n), to store all the permutations. While this method is straightforward and guarantees the correct result, it's computationally expensive and becomes impractical for inputs with a large number of digits. A more efficient way to solve this problem is by using a sorting-based approach. The intuition here is that sorting the digits of the number can help us directly construct the smallest possible value. For positive numbers, we sort the digits in ascending order. However, for negative numbers, the smallest value corresponds to the most negative number, so we sort the digits in descending order instead. After sorting, for positive numbers, we need to ensure that the smallest non-zero digit is placed at the front to avoid leading zeros. For negative numbers, the descending order naturally handles this. The rearranged digits are then converted back into an integer and returned. This approach significantly improves efficiency, as sorting has a time complexity of O, n log n, and the space complexity is O, n, to store the digits. It avoids the factorial growth of the brute force method and is straightforward to implement, making it a highly effective solution. An alternative to the general sorting-based approach is to use a counting sort, which can optimize the sorting process further. Since the digits in a number are limited to the range 0 to 9, we can count the frequency of each digit instead of relying on a comparison-based sort. Using these frequencies, we can directly construct the smallest or largest number based on the problem's requirements. For positive numbers, we ensure that leading zeros are handled correctly by placing the smallest non-zero digit at the front. For negative numbers, we build the number in descending order using the digit counts. This approach has a linear time complexity of O, n, as counting the digits and constructing the number both take linear time. Additionally, the space complexity is O, 1, as we only use a fixed-size frequency array. While counting sort is slightly more efficient than general sorting, it's less flexible and only works in cases where the input is constrained to a small range of values, such as digits. After evaluating the different approaches, the sorting-based method stands out as the preferred strategy. The key insight is that sorting the digits in ascending order for positive numbers naturally minimizes the value, while sorting in descending order for negative numbers ensures we get the smallest value, which is the most negative. Handling leading zeros is straightforward, as we just need to ensure that the smallest non-zero digit appears at the front. This approach strikes a good balance between simplicity and efficiency. It has a time complexity of O, n log n, which is much better than the factorial growth of the brute force method, and it's more intuitive and versatile compared to the counting sort approach. While counting sort has a marginally better time complexity of O, n, it's less generalizable and harder to understand. The sorting-based approach is easier to implement, works well for all valid inputs, and avoids unnecessary complexity, making it the most practical choice for this problem. With the sorting-based approach selected, the algorithm can be summarized in a few clear steps. First, we convert the number into a string so that we can extract its individual digits. If the number is positive, we sort the digits in ascending order and ensure that the smallest non-zero digit is placed at the front to avoid producing a number with leading zeros. On the other hand, if the number is negative, we sort the digits in descending order, as this will produce the most negative value. Finally, we convert the rearranged digits back into an integer and return it as the result. This step-by-step process ensures that we construct the smallest possible value efficiently and correctly, regardless of whether the input number is positive or negative. In this problem, we are tasked with finding the smallest valid number that can be formed by rearranging the digits of a given integer number. To approach this, let's first explore the brute force method. The intuition here is straightforward. We generate all possible permutations of the digits of the number, and from those permutations, we select the smallest valid number that satisfies the constraints. To begin, the first step is input preparation. We convert the integer number into a string so that we can easily extract its individual digits, and then we store these digits in a list, which allows us to manipulate them more conveniently. After preparing the input, the next step is to generate all possible permutations of the digits. For this, we can use a library function like Python's itertools.permutations, which provides an efficient way to handle the combinatorial logic. Each permutation represents a potential arrangement of the digits. Once we have these permutations, we move on to filtering valid numbers. At this stage, we convert each permutation, which is initially represented as a tuple, back into an integer. During this conversion, we ensure that we filter out numbers that do not meet the constraints, such as those with leading zeros or, depending on the problem's scope, negative values. With a set of valid numbers in hand, we then identify the smallest number by traversing through this list and using a simple comparison operation. Finally, the result, which is the smallest valid number, is returned as the output. To better understand the process, let's walk through an example. Suppose the input is number equals 310. First, we extract the digits, resulting in the list 3, 1, 0. Next, we generate all possible permutations of these digits, which gives us 3, 1, 0, 3, 0, 1, 1, 3, 0, 1, 0, 3, 0, 3, 1, 0, 1, 3. Then, we convert these tuples to integers and filter out invalid numbers, such as those with leading zeros. This leaves us with the list 310, 301, 130, 103, 31, 13. From this filtered list, we identify the smallest value, which is 13. Thus, the output for this input would be 13. This example highlights some key insights about the brute force approach. First, the complexity of generating permutations is exponential, specifically n, for n digits. This means the approach becomes computationally expensive as the size of the input grows. Second, filtering out invalid numbers, such as those with leading zeros, is a crucial step to ensure correctness. Finally, while this brute force method is straightforward, it is inefficient because it generates all permutations, even though only a subset may be necessary to find the solution. For instance, sorting the digits directly can lead to a more efficient algorithm. Additionally, we rely on specific data structures to implement this approach. Strings and lists are used to store and manipulate the digits, sets or lists are used to store permutations, and a separate list is maintained for the filtered valid numbers. These structures help organize the solution in a systematic manner. Breaking down the algorithm further, we can identify three key operations. First, generating permutations is handled by a library function, which efficiently computes all possible arrangements of the digits. Second, filtering invalid numbers ensures that we adhere to constraints like avoiding leading zeros or handling negative signs if applicable. Finally, finding the minimum is achieved by simply traversing the filtered list and comparing values. Additionally, certain edge cases must be considered. For example, inputs like number equals 1020 should produce 1002 as the smallest valid number, ensuring that permutations like 0120 are ignored. For single-digit inputs like number equals 7, the output is simply the same number. When all digits are identical, such as number equals 111, the result remains 111. If the problem extends to negative numbers, the handling of the dash sign during permutations must be carefully managed to maintain correctness. Here, we are implementing a Python solution for the problem of finding the smallest value of a rearranged number. We start by defining a class solution with a method smallestNumber that takes an integer number as input. First, we handle the special case where the number is 0, in which case we simply return 0. Next, we convert the number to its absolute value as a string, allowing us to work with its digits individually, and we determine whether the original number was negative. After that, we sort the digits of the number. If the number is negative, we sort the digits in descending order to create the smallest possible negative number. We then convert these sorted digits back into a string, join them, and apply the negative sign before converting the result into an integer. This ensures that the output is the smallest possible integer for negative inputs. For positive numbers, we sort the digits in ascending order. To avoid leading zeros, we identify the smallest non-zero digit and swap it with the first digit if necessary. This ensures the resulting number doesn't start with a 0. After arranging the digits, we join them into a single string, convert that string into an integer, and store it in the variable result. Finally, we return result, which represents the smallest possible value formed by rearranging the digits of the input number. Here, we start with the Java implementation for finding the smallest value of the rearranged number. First, we import the necessary utilities and define our solution class. Inside the smallest number method, we check if the input number is 0. If it is, we simply return 0, as rearranging 0 still gives 0. Next, we determine whether the number is negative by checking if it's less than 0. This helps us decide how to handle the digits later. We then take the absolute value of the number and convert it to a string, so we can easily work with its individual digits. After that, we convert this string into a character array, which allows us to sort the digits using the built-in arrays.sort method. If the original number is negative, we then reverse the sorted digits to arrange them in descending order and convert this reverse sequence back into a number with a negative sign in front. This ensures that we get the smallest possible value for a negative number. Now, if the number is positive, we proceed to arrange the digits in ascending order. However, we must ensure that the resulting number does not start with a 0. To handle this, we iterate through the sorted digits to find the first non-zero digit. Once found, we swap this digit with the leading 0 in the array. This guarantees that the number is valid and doesn't have unnecessary leading zeros. After making the necessary adjustments, we convert the character array back into a string and then parse it into a long type to return the final result. This approach ensures that we always get the smallest possible number when the digits are rearranged, whether the input is positive or negative. Here's how we approach the problem for a positive number, using the input number equals 310. First, we check if the number is 0. Since 310 is not 0, we proceed to determine the sign. In this case, since the number is greater than 0, we set is underscore negative to false. Next, we convert the absolute value of the number into a string, resulting in number underscore str equals 310. We then sort the digits of this string in ascending order, which gives us sorted underscore digits equals 0, 1, 3. Now, we need to address the issue of leading zeros. We locate the first non-zero digit, which is sorted underscore digits, 1 equals 1, and swap it with the leading 0. After this step, sorted underscore digits becomes 1, 0, 3. Finally, we join the digits into a single string, producing 103, and convert this back into an integer. The result is 103. For the next example, we analyze a negative number, with the input number equals -7605. Again, we begin by checking if the number is 0. Since -7605 is not 0, we proceed. Now, because the number is less than 0, we set is underscore negative to true. We then take the absolute value of the number, convert it into a string, and sort its digits in ascending order. This gives us number underscore str equals 7605 and sorted underscore digits equals 0, 5, 6, 7. Since the number is negative, we want the digits arranged in descending order to ensure the smallest value when negated. To do this, we reverse the sorted digits, giving us sorted underscore digits equals 7, 6, 5, 0. We then join these digits into the string 7650 and convert it to a negative integer. The result is -7650. Now, let's consider the simplest case, where the input is number equals 0. Here, we perform the initial check and see that the number is indeed 0. Since there's nothing more to process, we can directly return 0 as the result. To analyze the time complexity of this solution, we can break it into distinct steps. First, converting the input number to its string representation and taking the absolute value of the number is a straightforward operation that takes d time, where d represents the number of digits in the number. This is because each digit is processed once during the conversion. Next, the sorting operation, which is the most computationally expensive step, is performed using Python's built-in timsort algorithm. Sorting the list of digits takes d asterisk log d time, as timsort is designed to handle sorting operations efficiently. For positive numbers, a loop is used to ensure that no leading zeros appear in the result. This loop iterates through the digits and can perform at most d iterations, with each iteration being a constant time operation, resulting in d time for this step. Meanwhile, for negative numbers, the digits are reversed after sorting, which is another d operation. These steps together form the foundation of the time complexity analysis. Once the digits are sorted and adjusted, the next step is to join them back into a single string and then convert this string into an integer. Joining the digits into a string takes d time because we are concatenating d characters. Similarly, converting the resulting string back into an integer also takes d time since it involves parsing each digit. When we combine all these steps, the sorting operation, with its d asterisk log d time complexity, remains the dominant term. This means the overall time complexity of the solution is d asterisk log d, which reflects the efficiency of sorting as the key operation. For space complexity, the primary contributors are the string representation of the number, which requires d space, and the sorted list of digits, which also requires d space. Additional variables, such as flags or temporary storage for swaps, use only constant space, 1. Therefore, the total space complexity is determined by the size of the input and is d. Since no additional data structures are introduced that scale with the input size, the overall space complexity of the solution remains d. The memory usage is directly proportional to the number of digits, as it primarily involves storing the string and the sorted list of digits. When we analyze the time complexity further, we notice that the sorting operation dominates regardless of the input. This means that the time complexity stays O, D asterisk log, D, in the best, average, and worst case scenarios. The space complexity remains consistently O, D, in all cases, as the memory requirements do not fluctuate based on the input. This consistency in both time and space efficiency demonstrates the robustness of the solution across different types of inputs. To better appreciate the efficiency of this approach, let's compare it to a naive method. A brute force way to solve this problem might involve generating all possible permutations of the digits and then selecting the smallest valid number for positive inputs or the largest valid number for negative inputs. Generating permutations of D digits would require O, D time, and evaluating each permutation would add even more overhead, making it highly impractical for larger numbers. The sorting-based approach, by contrast, achieves the desired result much more efficiently. By directly sorting the digits, it avoids the need to explore every possible arrangement, reducing the time complexity to O, D asterisk log, D. Additionally, the space complexity remains optimal at O, D, as it only involves storing the digits and intermediate results. This combination of time and space efficiency makes the provided solution far superior to naive methods, particularly for large inputs. Let's start by discussing some common mistakes that can arise when solving this problem. One frequent issue is the incorrect handling of edge cases. For example, inputs like 0, negative numbers, or single-digit values are often overlooked, which can result in runtime errors or entirely wrong outputs. To address this, it's crucial to explicitly test your solution with a variety of edge cases to ensure robustness. Another pitfall is relying on inefficient brute force methods, such as generating all permutations without eliminating invalid ones early. This can cause your solution to exceed time limits, especially for larger inputs. A better approach is to optimize your algorithm by pruning unnecessary computations, such as skipping over duplicates or sorting to reduce redundant checks upfront. Additionally, misunderstanding constraints like failing to account for no leading zeros or ensuring the result meets certain conditions can lead to invalid outputs. To avoid this, carefully read the problem statement and implement checks for these constraints. Finally, improper sorting logic is another common challenge. For example, sorting digits in descending order instead of ascending order can lead to the wrong output. Always verify that your sorting aligns with the given requirements, such as producing the smallest possible value in lexicographical order. Another area where mistakes often occur is in unoptimized searches within permutations. For instance, using a linear search to find the next valid permutation is computationally expensive and unnecessary. Instead, algorithms like the next permutation method are specifically designed to handle this efficiently, allowing you to reduce redundant operations. Now, let's shift to some key insights for interviews. Recognizing patterns in digit manipulation problems is an essential skill. Showing that you understand how to generate permutations systematically, rather than exhaustively, can set you apart as a candidate. Also, interviewers look for your ability to explain why brute force is suboptimal and how you transition to more efficient techniques, such as sorting or leveraging mathematical patterns. Being proactive about edge cases is another valuable skill. Discuss scenarios like repeated digits, zeros, or the largest possible inputs, as this shows your thoroughness. Lastly, be prepared to explain any trade-offs your solution makes, particularly if it uses extra space, such as storing permutations in memory. Clearly articulating why the trade-off is necessary demonstrates a deeper understanding of the problem. To deepen your understanding, it's helpful to explore related problems. For example, the next permutation problem on LeetCode, problem number 31, is foundational for learning how to determine the next lexicographical order. Another useful problem is permutations, problem number 46, which focuses on generating all possible permutations of a given set. A more advanced version of this is permutations 2, problem number 47, which introduces the challenge of handling duplicate elements. Additionally, a commonly asked variation is to find the smallest integer greater than a given number using the same digits. This type of question tests your ability to build on the core concepts of digit manipulation and permutation. Now, let's compare some alternative approaches. The brute force method, which generates all permutations, is simple to implement and guarantees correctness. However, it quickly becomes inefficient for large inputs since the number of permutations grows factorially. On the other hand, the optimized next permutation algorithm is much more efficient, running in O(n) time, and directly computes the desired result. The trade-off is that it requires a solid understanding of lexicographical order and careful attention to detail during implementation. Another approach worth considering is the mathematical method, which focuses on digit manipulation. This can be faster for specific problems by eliminating the need to generate permutations entirely. However, deriving and implementing a mathematical solution correctly under time pressure can be challenging, as it often involves complex logic. Lastly, a sorting-based strategy can be very effective for problems that require finding the smallest or largest valid values. By sorting the digits appropriately, you can efficiently narrow down the solution space. That said, this approach may require additional checks to ensure constraints are met, such as avoiding leading zeros. Each of these approaches has its strengths and weaknesses, so the key is to select the one that best balances efficiency and implementation complexity based on the problem's requirements. Great work! Today, we tackled the problem of finding the smallest value of a rearranged number. We reviewed key approaches and their complexities, and we highlighted the importance of efficient digit manipulation. Keep practicing and exploring new problems to sharpen your skills. Thank you for joining, and we'll see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!